Okay, so hello everyone, and thanks for the invitation. This is my first time here, so very happy to be here at KFR. My talk was originally titled Advances on the Maldacena and Grinberg conjecture. We realized that we don't have any advances, so it's now just on the Maldacena and Grinberg conjecture. So I don't really have any results to present, but I'm hoping for some discussion to get some ideas from here. And please, this is in that spirit, I hope this is less of a talk and more of a discussion, because otherwise it would be, as you can see, a very short talk. So let me start. This is the project that I will be presenting, such as it is, and led by my PhD student Arundhati and my collaborator Parijat. So Maldacena-Grinberg conjecture, what is it? So from the early days of ADA-CFT, people have been asking, what can we say about the black hole singularity in the bulk from the boundary correlation functions? And Maldacena and Grinberg addressed a slightly different question, which is what they showed is that the thermal one-point function, so the one-point function in the thermal state, encodes the path from boundary to singularity, in the sense that when you have some boundary primary with the large conformal dimension, then the one-point function of that in the thermal state kind of behaves in that limit. It goes to some exponential of the mass of the dual scalar of this, which is also large because the conformal dimension is large, multiplied by the distance from the boundary to the horizon, and a phase which depends on the time taken from the horizon to the singularity. So all on radial geodesics. So this is the statement of basically the conjecture. This is the leading part, and then you can have subleading parts, which are some polynomial in M. It's just some primary in the CFT. Sorry? Right. Right. Yeah. Yes. Yeah, let me show the picture. Yeah. Yes.
Why am I going from the boundary to the bifurcation point and then to singularity? Why can't I just take any part I want?
So this, you follow a radial geodesic. That's where it comes out. But we'll discuss why that happens. So the idea is like you kind of go to the horizon, and then you have to analytically continue, because you start from a Euclidean horizon, you go to the horizon. Right, that's a good question. Yes, the answer is yes. This is the shortest path. So if you do like a proper analysis of steepest descent, this is the path you get. In the paper they do that. So you can do like I won't talk about it, but you do a Picard-Lipschitz and you get, this is the path you get. Yes. Yes. That's a good question. They did it for a scalar. So they were always considering something that's dual to a scalar. They did not consider what happens when there's a spin, but as we'll see, the kind of derivation should go through for a spinning field also. I think so. I've not worked it out, but let's see. Let's see the proof, and then you can figure this one out. Well, that's a good question. I don't know the answer. Okay. So let's proceed. So this was the setup. So this is the kind of action you take. And let's forget about this term for the moment. Let's just look at the free action. And this free action, you will see that has a symmetry of phi goes to minus phi, which means that the one-point function of phi would be 0, which means by extrapolar dictionary, the one-point function of O would be 0. So for that, you need to add something that breaks the phi goes to minus phi symmetry. And the term they chose was Wild tensor squared. So you have the scalar field coupled to Wild square. Sorry? It works for other couplings also, as we will discuss. Yeah, but this is what they chose in the original paper. Yes. Yeah, because now you don't have that symmetry of phi goes to minus phi. You see, there's just one phi here. So if you take phi goes to minus phi, the action is no longer symmetric under it. Yes. So if you have that symmetry phi goes to minus phi, it means that the 1-point function phi would also go to minus of the expectation minus phi. So it should be 0 always. So unless if you want something non-zero, you have to add some way of breaking that symmetry. Right. Yeah. So yeah, W square is turned on everywhere. So yeah. So the role of this W square term is basically to provide a source for the 1-point function. And this is how you would calculate the 1-point function, where you have, this is your bulk boundary propagator, this is your source, and this is the expression. And we'll see that it doesn't have to be Wild square. We'll see in other examples. Yes. I will, yeah. Yeah. Sorry. It works even in 3 dimensions, but not because Wild square vanishes in 3 dimensions. So you have to have some other thing. Yeah.
Like complete the squares, phi minus something square, coupled with W square kind of thing, and then make it of the original form.
I see what you're saying, but yeah, so that would have like some kind of weird 1 by W term or something outside. Yeah, I don't know. Yeah.
So the phi minus something, that something will be expectation value.
He wants to complete the square phi plus something W whole square minus some W dependent term. Yeah, I think one can do that. I'm not sure. Yeah.
But they have done something.
This is what they have done. No. I mean, you're saying that would be a step in the calculation, right? Completing the squares. I mean, you could do it that way probably, but I don't see why the results would be different. Yeah. So this is all at the same time because you're just looking at a radial, just 1 point. Yeah, it's the usual kind of bulk boundary propagator value. Yes, yeah, this is a Euclid. Sorry, yeah, I should have said that. Yeah, it's a Euclidean integral. Okay, yeah, good. So now the idea of how one goes about proving this, or the argument behind this is you take a heavy field, you're looking at a heavy field. So you can take this kind of an approximation for the propagator, basically like a WKB approximation where L is your geodesic length. And then your integrand is has this term and the W square term. And so this is, yes. This is the conjecture. So the 1-point function has this form. So this L horizon is the distance from the boundary to the horizon, and this is the time taken from the area. Sorry? Okay. Right. So the integrand looks like this. So there are these 2 terms competing here, which is this guy and this guy. And the next step is you want to solve this integral for the 1-point function using a saddle point approximation, which means that the derivative of this thing has to go to 0. And for the saddle point, there are two terms competing, which is the derivative of the geodesic length and the log w squared. So this gradient, this guy, and this other guy. Now what happens is this guy, of course, wants to keep the geodesic length short. If there's no, nothing stopping it, it would want like the shortest possible geodesic length. Whereas, if we compare these two, this is a derivative of geodesic length, which is order 1. So this is of the order of mass. And the derivative of log of the y square is order 1 by r. So this term more or less always wins because m is large, except when we go close to the singularity, where this kind of starts blowing up. So when you go close to the singularity, what happens is, yes. So I'll come to this. So suspend disbelief for the moment. Think of this as the whole space involved. And so the idea is that w square would diverge near the singularity. That's the only place this dominates over this, if this is large enough. So as you go close to a singularity, the variation of w square, as it is getting large, that also varies rapidly. So you get a saddle that will be close to the singularity. Yes. This is the renormalized propellant, yes. So, but that has to do with the boundary. Right? Okay. It doesn't have a saddle point. Yes. Right. It will have endpoints, but it will not have a saddle point. So yes, so this is the idea. So what you actually want to do is your integral is a Euclidean integral. So it is integrating outside the black hole horizon, but you want to continue the geodesics inside. And so for that, the choice they make is they make the mass slightly imaginary, which corresponds to this kind of choice of analytic continuation of the geodesic. And then you find the saddle location for this complexified geodesics. And then it turns out that the saddle is at some tau star, which is tau s is the singularity time, and c is some constant, so it's tau star minus ICM. So it's some point close to the singularity called large M. If you take m goes to infinity limit, the saddle is exactly at the singularity. And then when you evaluate this integral now at this saddle, this is the answer that you're going to get. And yeah. So you start with your Euclidean cigar, and there were initially you have the integral. You will initially have two geodesics which contribute to the saddle in the Euclidean integral. There's a short geodesic and a long geodesic, but when you allow which both end at the horizon. So when you allow this extension, you will find that both of them contribute to the actual final path of steepest descent, which has this kind of form. It's come from here, so it's L horizon plus I tau. So you start, yes, so you go up to the horizon, and then you allow this continuation. See some constant. When you solve for the saddle point, you get some constant.
Then that should add to the right.
Which one? So this is I. This is I here. Yeah.
Always already have an I.
Yes.
And I will take the
Right.
part.
Yes. But you take the m goes to infinity limit. So this is just tau. Right. So let me pause here for any other questions, because this is kind of the proof.
The radial.
Yes. Yeah, so you start with the spherical symmetry. So this integral basically boils down to a radial integral. So you just have an integral over the radial line. And that's why when you are integrating, you're just, when you're continuing that in that one variable, which is the radius.
Right. As a kind like.
Yeah, it's all static. It's always a static black hole. Yes.
I see. So the question that I asked was
Yes.
not about, so I should not think of it as a particular path being taken. It's just a complex number.
Yes.
X coordinate is this, Y coordinate.
Yes. Yeah, that's it. Yes.
It doesn't matter how you are going there.
It doesn't
That
matter.
is
Yeah.
somehow some sort of a heuristic thinking that you go for the Euclidean propagation, you get this way.
Yeah, that's just yours. Yeah.
But the saddle point is just a complex number.
Just a complex number.
Plus,
Yeah, that.
that.
Yes. Yeah. That's correct.
So that tau is very close to singularity.
Yeah.
Thinking of that as actually being singularity.
Yeah. Okay. So now this is kind of the argument for why you should get the Maldacena Grinberg conjecture.
But is it that
Yeah.
as the infinity that will move closer and closer to singularity?
Yes.
How to see that?
Yeah, from this equation.
Oh, tau s is the time to singularity.
Yes.
Right? Yeah, and then tau star is a little less than that, but in the end, you
Yes.
will
It goes exactly to that. Yeah. Okay. So this is the argument. Now, how do you check it? It's like now it's you can see how would you check it from a particular case. You pick some ADS black hole background. You pick some interaction to act as a source for the one-point function. They picked Y square. Then you compute the one-point function holographically. And then there's the left-hand side. This is your left-hand side. The right-hand side has this. So you compute in this background L horizon and the time to singularity. And you check if the left-hand side, which is this, and this limit, and the right-hand side if they match. So you take a black hole background, you can do all of these operations. And that's how you would check. Yes. Then there's no singularity, right? Yeah. Yeah.
In that case, we expect this to be 0.
I don't know. I don't know the answer. So then you're saying that that is a situation where there's no analytic. So there's no like a singularity. Yeah. I haven't checked. So then I guess, yeah, one would have to do the saddle point analysis, right? In that background. Yeah, the temperature never entered the analysis. Sorry? Yeah. L horizon will, depend on the background, obviously. Yeah.
Sorry, what I was saying was.
Yeah.
That is something this is the large 1-point function. Is there some and then square sitting somewhere? Refactor in the square?
There's no n square sitting somewhere, but of course we are assuming this is a.
But we expect that at any finite temperature, even small, 1-point function may be generated, right?
Yes.
Then when it is below that docking phase transition, where you don't have this kind of geometry.
Yes.
Over.
Yes.
Then what is the expected answer? The thermal radius, does it give some expected answer?
There's no expected answer. No one has checked, but.
Because I should put this kind of integral there.
Yeah. I would assume there's no saddle there.
No saddle.
I don't know. I mean, that would be the expected. There's no special point. So. Oh. Yeah. That's the.
What is that?
W is wild tensor. No, why should it be 0?
So you're comparing, you're looking at the 1-point function of an operator. Yeah, and your question was what?
So this is Maldacena and Grinberg. My question was, what if the temperature is below the optimum phase condition, where the below is spread not by a black hole geometry, but by radial geometry? In that case, what is the expectation first of all, and second, can we see it using this kind of analysis?
So presumably you get order 1 rather than n.
Is this order and square?
Which this meaning
After patient, How to see that?
Well, there'll be let's say we're looking at a scalar field, let's say, delta. There's an action for the delta, which has 1 over g outside. You're doing the calculation for that action without the delta. But you're doing some geodesic. That's the 1 over g.
That's the exponent. The exponent.
Yeah, I suppose the exponent then.
Because the formula is just that, right? That's the hidden diagram there. You just have to do that. 1 point function in the diagram, right? So is there a 1 by t? Yeah, alpha. Alpha is 1.
Alpha is the coupling between the scalar field and the wild tensor.
Yeah.
Yeah.
So that's it, the exponent, right?
Yeah.
That's where you put this happen.
You turn on a source, there'll be something in the exponent. Then you differentiate it. The 1 point function will be your x. That's just nothing.
Yeah, I'm making that alpha. Yeah. But I'm technically not able to understand why is it coming down.
But I don't follow the calculation.
So the calculation is that you are writing this 1 point function like that. That's like a written diagram type calculation. Right, W square is sourcing this 1 point function to the
So there's 5w squared W.
5W square.
There's a 5w squared.
And this integral will be computed by a saddle point function. Saddle point.
Excellent.
The value is large. Alpha is kind of like a number.
Excellent. So it's like sorry.
Mhm.
So isn't the thing that you're doing, you're turning on a source for the scalar field on the bottom?
Right. There's a W square.
No, I am. But suppose I want to compute one.
Oh.
I compute a source in the bottom. I turn on a source in the bottom. I compute the action and then I differentiate with respect to the source. Right. So I want the linear term in that source. Right. So that you'll be computing an action upstairs, which has a 1 by g outside. And then you differentiate the 1 by g upward.
The other way to think about this thing of O as like the boundary limit of the bulk phi. So roughly you're calculating the 1 by function of the bulk phi operator, just taking it in boundary. And that 1 by function, when you pull the W square phi down, will be 50. That's now for the talking about this smaller temperature.
Now talking about the smaller temperature, all actions are order 1. Right, because it's all 1. Right, it's all from, there's no classical actions. It's pure ABS. And then there's a bulk 1 loop, the gas. That's order 1.
How did one see from this formula is still you, except the integral is now formulated.
See, these formulas, what exactly now?
First point function.
1 point function of boundary operator. Key is what? Power to boundary. Nice. Power to boundary. Okay. So basically this W is not turned on classically.
Oh yeah, so that's how you.
Yeah.
That's true. W.
Yeah, because W is just AEs.
Okay, the W.
W is just 1 loop.
So then that's fine.
Yeah.
No, gas.
Okay, I see. So that's another. Okay, that's another way to take that. Right? We have microscopic computing.
Yeah.
That. Okay. But actually now, earlier you said that this term, the W term only becomes the talking when W becomes large, right?
Mhm.
You understand the other thing.
Yeah.
But there is a 1 by D, right? So it's a bit.
Yeah, but W still like blows up at the singularity. So why is that
When the 1 will go across.
yeah, it's outside everything, right?
Right.
So when you do the saddle point analysis, the 1 by G unit is earlier. Yeah. Okay. So so these are the scenarios where this was checked. So in the original paper, they checked like planar radius black brane, BTZ for this kind of coupling, and 4D and 5D Schwarzschild black holes. So you check in the sense of, in this sense, in the holographic sense. So you do this holographically, you compute this thermal one point function, and then you check. Yeah. So now they do it exactly.
Computer music way big equation, that's all.
Yes, yes.
And then check that the geodesic saddle point, this particular geodesic that goes to the singularity,
Yeah.
correctly it produces the weight.
Yeah. So you no longer do a saddle point. Yeah. So you no longer do a saddle point analysis anymore. You do it holographically, and then you directly take this limit in the exact answer that you get. So whatever one point function you get, which is hypergeometric something something, you take this limit and you check if this is what it is. Yeah, do the integral exactly instead of a saddle point. Yeah.
To check the right way of doing the work, the right saddle point of the work. Yeah. That is a bit weird, right? Saddle point is weird, but it's complex. Complex, it goes to a singularity. Yeah.
Right. And then Justin and Srijan Kumar, they also checked in a bunch of cases, and they, instead of wild square coupling, they also checked for Gauss-Bonnet coupling, and this also works for all of these cases. Yes. Yes. Yeah. So he also did some large D, and there was some computation which I don't know about, but yeah. So this particular paper, he was just looking at this term. Yeah. From the CFT side, I have not seen checks from purely the CFT side. Yes.
In a BT-set black hole, we expect once again such a one point function.
Yes. So you don't take a wild square, which is 0. So you take some coupling like this. And you take like a BT-set black hole, which is like a periodic in space.
What chi?
Chi is some light field. So you add your heavy field with couple with some light chi-square field.
But chi is 0, though. Is that accurate?
Right. So that's why you want to take like, no, chi is not 0 in the BT background. So you also want to take like a periodic boundary conditions, like a torus.
Sorry, I was thinking BT there is just orbifold of ATI.
Mm-hmm.
The only non-zero field there is the.
Okay.
So why is chi non-zero in the background?
Chi is some, sorry, why should it be 0? It's
because all fields except metric are converted to 0 and ADS, and everything. And therefore, if you take an orbifold of ADS, it will continue to be. What is chi?
chi is some scalar, some scalar. Yeah. So you are also taking like a torus. So you are not taking like the usual BTZ, but you're taking something with periodic boundary conditions. And in that case, the wave is non-zero. Yeah, I don't know the answer to that question.
Yeah. If that is the case, then maybe probability is also you can create such a configuration. From 0 from and from B.
Yeah, I think it's so. You don't have to have wild square. You could have like phi n coupling in thermal ADS. Yeah.
Yes,
Right.
let's see in our hand what we need.
Yeah.
Be what was dictated by the geometry to
Yes.
And then,
Yeah, I understand your question. Yeah, yeah.
then what are
Yeah. Yeah, I don't know, because yeah, if there was like a pure CFT side derivation for this, that would be more clear, I think. But somehow, like all these derivations need the bulk to proceed.
I think that in the case,
Hmm.
the prediction is for particular type of CFT.
No. Yeah. Yes, you had a question? Okay. No, they checked for static, and then these guys checked for rotating. Yeah, same coupling.
Why is that? Non-zero and uniform is part of the probability concept. Yeah, then we're not complete. Yeah. So, exactly.
Hmm.
The change of
Sorry. Yes. Hmm. Yeah.
Yeah, that one is real. So you are like getting some time.
M has a slightly imaginary part.
So from the yeah.
This, so you take the epsilon goes to 0 limit before taking the boundary, I think.
I see the
No, see some constant. Yeah. The one from the future and the past. Ah. They,
But I mean, you get some in the internal time, you get a why future?
yeah, I don't know the answer to that question. Yeah. So I think they get just one singularity, but maybe they're not considering the past. Sure. Okay. So then there was this paper by Kaustubh Singhi from ICTS, who extended the kind of argument from wild square to just phi n scalar interactions. So what he showed was he considered planar ADS black brane, and then he showed the following, which is that you just take a self-interacting field phi to the power n kind of interaction, and then you get the same one-point function relation. And this also generalizes to n correlators, n-point correlators. So instead of 1 point, if you take n points, then this correlator also kind of factorizes, and there are n powers of this term. And then you can further generalize to heavy light mixed vertex. So you have a light field chi to the power m and some heavy field n. And then if you take like n point or some other, I use the same n and m here, but some other, whatever you want to take, n points of this guy and some m points of this guy, and find the correlator, then it's only the heavy field thing that will come here, and the m factors will be in the prefactor. So this dominates. So this is what, yes. Sorry. Yeah, so that was a question, yes. Go ahead. This kind of interaction, phi cube or phi cube for 4. Yeah, the thermal one-point function. Yeah. Sorry. Yeah, L horizon is the distance from horizon, boundary to the horizon. Yeah. So it will depend on the temperature. Yes, black hole temperature. Yeah, this is the information. Sorry, Abhijit. Yeah.
No. It's the best for
Yes.
explain the scalar field.
Yes.
In the ball.
Yes.
Previously was W square phi, right?
Yes.
So, W square changed in the bulk, and
Yes.
then I kind of
Yeah.
saw where this.
Yeah.
But what does it mean when you have this quantum field?
Yes. Not really. So I will try to give some explanation of, what they have done and what I understand of this. Okay. So yeah, we'll listen. Yeah. Yes, same picture here. Sorry. Yes. So this is the endpoint correlator, but you see this in this action, it is n multiplied by this. So for each 1 point, there is this factor, same factor here. Okay. So n of them. Okay. So let's do the saddle point analysis for this. You take pi to the power n interaction, and so then your integrand will look like this, where this is your kind of action, and this is the geodesic length once again, and these are the prefactors that you get from. Sorry. So you're writing the integrand of this 1-point function as e to the power minus mf SW, and SW is whatever appears here. So this is your SW, this is your L, and this is some prefactor. So this is a subleading term that you get from WKB approximately. This is a WKB subleading term. So what they do is a WKB analysis for large M. You put this whole thing in the equation of wave equation, and then you get one subleading term.
Length of the horizon and other W square.
Yeah, so there's no W square here. There's only a phi n interaction. This is a different scenario where there is no W square. There's only a scalar which is self-interacting. This is the prefactor that you would get if you just put this in a WKB analysis, take large mass. So this is the large mass analysis of Klein-Gordon equation. So that will have like a leading order term, leading order piece, and a second order piece. What is the action? It's the Klein-Gordon action for a massive scalar with this kind of interaction, pi to the power interaction. Yeah. Okay, so now the endpoint correlator has this kind of form. And now you're seeing a competition between this geodesic and this kind of a term. Okay. And then you do again the saddle point saddle condition. You get an equation like this, and do the same thing, and you get something like this. All right. Yes.
That's the initial saddle point.
Sure. Yeah, this one.
Yeah, exactly. Yeah.
Yeah, this one. Yeah.
That's the integrand which goes in the. That's the integrand that goes in the Witten diagram, right?
Yeah.
The wealth boundary property is from 0 to x, so that's that contribution.
It's like okay, the integrand, yeah, okay.
Integrand I of x. Right, that's like k times w square. K is written as e minus ml. So now that it becomes the integrand m large, and then you do the saddle point. So it's just a matter of computational saddle point. Other than
you're saying a saddle point is a geodesic that ends at a point.
yeah, saddle point is of that integral, which has a geodesic action ml, and that x star just happens to be very close to that thing. And then you evaluate the action on it, and you get that Maldacena and Grinberg answer.
But in the end, the saddle point n is like a. Do you think that has an?
No, saddle point is x star is saddle point is this is written diagram. You're just integrating over a bulk point with the bulk point sourcing k w square of x. So the integral is integral over the bulk of k 0x w square x. That's what you want to integrate. And x star is very close to that. Now you just evaluate on x star this action, and you get this. This happens. X star happens to be complex, and then you get You just put it in there, you get ML X star, but X star is complex, so you get that.
Yeah.
So interesting. Yeah, with the side on.
But finally, geodesic is any.
Right. So, yeah, but it's just the evaluation of the action there. You're just evaluating the length of a geodesic to that extra. Exactly. Yes, you're right. That the geodesic, you can think of that as just being a indicator. Because that's the saddle point.
So you are extremizing over X, which is in the bulk,
Right.
right?
Yeah.
Now, this would give a point rather than a path.
Yes. That's the extra point. That's the extra point. You put it in there, you get L of 0 comma X star. That L of 0 comma X star happens to be L plus I tau. Where L now is this immediate line.
Okay. But it's still giving you a point, not a path to that point.
No, yeah, it's still giving you a point. You just
Yeah.
evaluate it. You get the action that you want.
So the integrand is a geodesic, and this W square is just saying where it will end.
And it doesn't go near to the, I mean, what parameters does it go near to the singularity?
Yeah, this is the thing.
M.
This is the singularity, this is the mass, and this is some constant.
So the parameters n goes to infinity goes.
Yes,
to the
yes,
singularity.
right.
Okay, so this in the geodesic approximation goes to the singularity. And geodesic approximation is accurate. So it's a geodesic that goes and it's the singularity. As far as geodesic, fine, got it.
There. It's just happening to a standard saddle point calculation.
But your point was that it needed some derivative.
You need to balance this. You need to find a saddle point. So you differentiated W square, right?
Yeah. So this was the,
But
yeah.
So you differentiated W square, there was some order of analysis there. That goes by n, while this goes by order 1, and then you need to go towards the singularity for which you have the second term balance.
And will all kinds of interactions go up in the singularity?
Yeah, that's what I felt. I can imagine a copy square, but like 5 cube or.
yeah, so, yeah, so let me finish this part. Yeah, so this is the phi n interaction, where you have now have is like a geodesic length and the prefactor coming from the the subleading term in the WKB approximation. So now this is your endpoint correlator, and what you now have is when you again find the saddle point, you get something like this, which again goes to the singularity, which is in this W coordinates, which is these are the coordinates being used. In these W coordinates, this is where the singularity lies. So anyway, so for large M, the geodesic term dominates, you get once again the same kind of thing. Yeah. Yeah.
So the previous case, there was this length piece
Hmm.
and W square piece.
Yes.
Here, what is going on?
Here there's a length piece and there's this subleading piece.
Where is that?
Just from the WKB analysis, now you keep the next order piece. The phi n is there in the term, but the origin of this part is just from doing WKB analysis and keeping terms till the next order. Yeah. Is this a geodesic propagator going to the singularity? For phi n. So there are like a lot of legs going to the, yeah.
And meeting each other at point X, and that's what.
Yeah, that's the, yeah.
And then that just happens to be very close.
Yeah. That's the picture. Yeah. So, sorry, your question. Same question. Okay. So what I think is happening here is this.
But I still don't understand why it will go close.
Right.
There was a very sharp one.
Yeah. So this this is what I think is going on. So this is not in the paper, but this is kind of what I think. So the prefactor is so I wanted to understand exactly like why, because the wild square is obviously weighing the singularity, but what is happening here? So the idea that I have is, suppose you have, so the prefactor is this Van Vleck moderate determinant, which is a geometric interpretation in terms of how the density of the geodesics the density of geodesics basically. So this is the Van Vleck moderate determinant. It depends on the distance between geodesics. So it kind of is related to the expansion parameter. So the derivative of this relates to the expansion of geodesics. So now if you put this in the Raychaudhuri equation, what we know is this expansion parameter blows up as we go close to the singularity. So what's happening is this, all these geodesics get closer and closer. So this Van Vleck moderate thing blows up near the singularity. So that may be what is going on. That gives the kind of compensating factor for the geodesic length to end at the singularity.
Why are we getting bulk propagation?
Why are we looking at the, so this point can be at the boundary. So one of these points can be at the boundary. Yeah. Yeah. So one of the points is at the boundary because we are looking at K, which is the, like, yeah.
Delta provides some
Yeah.
load up. So it's like even saddle point approximation, you have
Yeah.
another one term,
Mm-hmm.
which is blowing up at the saddle point.
Yes.
How balance that order will.
Yes. You have to have something.
It sort of brings me, the condition for WTV to work is that the fractional change of momentum is small in one. Right, the one loop correction for WTV is like this time. Now near a singularity, everything is changing very. At the singularity changing infinity. So it seems reasonable that this condition will break down here. That's it. That's down in the answer. Yeah. So he's trusting one loop where you cannot then. Because one loop is important to loop that. Yeah. But he's saying that this will repair. Alright, treatment theory is for non-geodesic.
The Raychaudhuri treatment here is not for non-geodesics. Yeah. Okay. So so this was the review part, and now just want to talk a little bit about what we're trying. As I said, we don't have any results, but this is what we're, yeah.
What sources? Well,
Yeah. So
that's going to come.
yeah. So here, basically, it seems like just the subleading part of the WKB that comes from the WKB approximation.
That is good. But
Yeah.
what was the source?
Oh, yeah.
Okay, got it. Got it. You just compute. You can't do with a 5P and you can't do a 1 point.
You can do a 1-point function. Yeah, you can do a 1-point function.
So what is
This is
the
a
source?
planar black hole. The source is just phi n. The source is just self-interaction.
I didn't understand that.
Yeah,
So,
sorry.
is it now a loop diagram? A loop diagram, is it like there's 1 5 going and then the other n-1s are looping into each other?
No, so again, this is the same calculation where you just take a saddle point and then you do, you take, yeah,
So say you have 5P and interact.
yes.
Phi is 0 in the background, right?
In a planar black hole?
Phi is just some scalar field.
Yeah,
Then a black hole rolling metric system, at least.
yeah, yeah.
Okay. If we're working in perturbation theory alpha prime. So now what is the source for alpha prime? Are you saying the phi to the n-1 is a source?
Yeah,
of
phi to, yes, yes.
But then that has to be a quantum source. I mean,
All right.
unless you're saying phi is non-zero.
That's the 1 point. That's the one loop determinant.
Hmm.
Of getting against the shadow.
Yeah, exactly, yeah. So that's why the one loop determinant is, yeah.
Right.
That's where this part comes from.
What would be the feedback?
Sorry. Yeah, there will be some coupling constant here. Yeah, it will be outside in all of these things. Yeah. Yes. Yes. Right. Yeah. So your question is about whether one needs a loop or something.
Yeah, that's what.
Yeah. So I only know this calculation in this sense of because what they did was just starting with a geodesic approximation and doing it and then doing the saddle point analysis. So the Witten diagram was not computed, but so I'm not sure which exact Witten diagram this corresponds to. But the only thing is that this Van Vleck-Moret determinant part that comes as a subleading order should be like some kind of a quantum loop correction. That's why it usually comes from Feynman diagrams. Yes, yeah, it's a good question. I have to think about it.
There's a IQ, let's say, the IQ matters that calculate both. Get that in the contact diagram.
Now, is there a sense in which if you have a 5-cube diagram and you compute the 3 points, is there any sense in which it's dominated by? That's a very different picture from what that has like. Is there some sense in which that is dominated by? No,
That seems to be the discussion. But now I'm saying that each one of the boundary operators has its leading.
Yeah, it was the same side. Yeah.
The correction.
and this is I very naively I would have thought that this M is large, so that you've got 3 points. They will try to make a triangle as close as possible. If they were small separated, they would make very close, and that what happens near the horizon would be totally red. Maybe it's a subleading side. Not unlikely to me that it's a leading. Right, at least if distances are close,
Right.
then it should just take the power law of conformity. Which sees nothing like this. So I thought the 1 point function was somehow different because it's the only thing that
Maybe in some limit where the distances are comparable to temperature.
yeah. So it feels like there are 2 contributions. There's connected contribution. Okay. This feels almost like a disconnect.
Yeah.
Right, because the final answer is just 1 connectivity.
Yes.
Each guy on his own. Right? Interaction is playing very little role. So maybe it's sort of like there is the path that is end point. Right? And then there is the interaction.
There is some analysis of that sort for 2-point functions, right? Maybe what we said. Where they do that and then they find that in some particular phase they should have connected some contribution and the other. Maybe as we increase the temperature, we notice it's go and fall off into similarity.
Oh, annoying. Like going tangle. Like to connect to them. Yeah. Yeah, that sounds possible. Possible. That will be a case.
It would be a similar thing as temperature.
Or as a function of this.
Yeah.
Yeah.
Yeah. What is the?
I mean, it seems clear, at least I feel intuitively that the points are nearby compared to the distance to the horizon temperature scale, they will just connect that among themselves. But which point is that now if you take the points far away from the scale temperature, there's a benefit to it. Each geodesic can just go into the singularity itself rather than connecting up with something very far.
This is in case you're computing endpoint function.
Let's talk about computing endpoint function with a phi to the n direction. And let's also, for a moment, I don't understand how a phi to the n is computed. So let's also assume that there was a phi y squared interaction for each.
Then each one will do something.
Then each one will, there's a possibility for each one. There's a possibility for connecting up. And which one is more favorable will depend on the time. If that sounds reasonable.
I thought we're debating how each thing doesn't
Well, I mean, can you imagine that each thing does its own thing? If phi has a non-zero variable. So let's say that it's true that it's some higher order that will have everything gets non-zero variable. So let's imagine that in a backward background in string theory, every scalar field has some non-trivial property. I would imagine that will happen in the order quicker. No, even classically, that will happen better. Because anything within these things will, why not? So if phi itself has a non-zero value in the background, then even each one can do something with phi to the, because we use the phi to the n minus 1. Right? That's the fun. Actually, the place where it sounds unreasonable is the BT set. Because since that's an orbifold, a classical order sounds unlike it, unless the orbifold is near the orbifold. But other than that, sounds good.
Sorry, but the string of phase transition is different than the Hawking phase transition, which is that let's say you are in Kajuri radius, then there is no scale, right?
It's definitely different from that. I mean, we could just be in the high temperature phase, and as a function of distance, we can be there. Yeah, a function of distance. There's definitely. I mean, can.
Yeah, let's think of it as function of distance.
Yeah.
And then problem.
Right. So what we are trying to do currently is to see if we can deform the background a little bit and if this still holds. So what we want to do is take whatever black hole background, deform it a little, and the geodesic length will of course change. And similarly, the 1-point function will also change. And this is del epsilon is what I'm calling the change at first order. And we want to see if the changes match. So if this first order change in the 1-point function matches the expected first order change in the geodesic length. So you take the BTZ metric is the one we're using. And here, the interaction considered is phi into some light field chi square. And then this is a kind of 1-point function sourced by this guy, where this is the chi square green function, bulk green function at the coincident limit, renormalized. And then under, sorry, which back? This, yeah, so this is yeah, so this is you take the green function of chi square and you subtract the singularity divergence piece.
So
it's a, yeah.
Quantum, yeah.
Yes. Yeah, so 2-point function in the coincident limit. Yeah, so the linearized variations you can calculate. So for the bulk boundary propagator, it will now satisfy this kind of equation. So you can break everything into perturbations at epsilon order. We're not turning on any source. So let's be agnostic about what is delta G for the moment, and then I'll come back to this. Yeah. So I'll tell you what we're doing. So suppose there's a change in metric somehow, which is delta G, and then you want to change this guy to some epsilon order, all of these changes, and then just usual perturbation theory where the change will now satisfy this equation with some source. And so this one will now have some homogeneous piece plus this kind of inhomogeneous piece, which you can solve using bulk green functions. Similarly, for this coincident two-point function thing, you can do a calculation, you get something like this in first order. So the one-point function will have, the change in one-point function will have all these pieces from perturbation theory. There's no half there, and this bracket should close. Right. And then you want to compare with the first order change in geodesic length, which would be something like this. And then what we are doing is, ideally, we should introduce some source, solve Einstein equation, etc. We're not doing that. We're just, as a first check, we just want to see that if we just take one of the metric components and change it by some some function which is r to the power minus p outside the horizon, so it falls off, it doesn't disturb the asymptotics, and some smooth function interpolating between whatever horizon value we have, and goes to zero at singularity. And we want to check simply the part about the length change to horizon. So if we go back to this equation over here, this one. So this part is again the one-point function. So you take it here and you just look at the real part. So that is your this. and the status of this problem is in progress. So we are trying to like work out all the pieces and match. So it's something we're still doing. And so let me conclude. So that's about it. So Maldacena and Grinberg conjecture relates thermal one-point function to this time to singularity. So you have to have some kind of interaction, but otherwise, whatever interaction you have, it seems universal. And we are trying to see if we deform the metric a little bit, does it still hold? So with that, I will stop. Thank you very much for your time.
Is there a geometric interpretation of first order information?
So the geometric interpretation is that this kind of thing is can be achieved by a gauge transform, a diffeomorphism that doesn't vanish at infinity, but it's smooth everywhere else. Some power, some number.
The dimension.
No, you just choose some power.
People write things for
I have not seen. Yeah. Yeah. So people have done charged black holes. People have done charged black holes, but I didn't see chemical potential entering the picture. So charged black holes, I think, was, yeah. So this was done by, this case was done by Justin.
So, going back to Drew's question, the answer for your one-point function is an oscillating function of the mass. Is that right?
Right.
So it goes to zero at some point? A special value to the mass?
The one-point function.
Is it like a cosine or a sine?
Yeah, I'm not sure. Yeah.
I think that in the paper it's one more side.
Yeah, it's usually some cosine or sine. Yeah. Okay. Yeah. So that goes, yeah, that's a sine. But since you take this kind of limit, so since you make this m slightly imaginary, that's what picks up the e to the power I part.
Is the final answer 1 over sine or sine?
I think it's
The final answer is a cosec, if I remember correctly.
Cosec, 1 over.
Yes.
Where did that?
So I mean, it's not easy to say. If you calculate the 1-point function, for example, for BTZ, you will get a final answer which will have a cosec term.
No, the
Oh, from the geodesic length business.
complex part that you had as who was suggesting complex particulars, that sounds like a cosine, sine. Right? How does it come down to them?
Yeah, sorry, I don't understand. So you're saying that, let me go back to this part. So this is the part you're talking about.
Yeah. So I thought it would be e to the power m times l times this plus maybe complex particulars. So it's sort of like e to the power minus l horizon times sine of m tau or cos of m tau or something like that. But you're saying 1 over that.
No, 1 over that was when you calculate the exact 1-point function and
Okay,
so on.
so that's okay.
So yeah,
That's it.
yeah. So here what was done, okay, so you probably don't understand the question. So here what was done was you make a choice of whether you want to make m plus I epsilon or minus I epsilon. So they chose this one, and this corresponds to, in the e to the minus ml term, this corresponds to picking L horizon plus I tau, because that's the one that will converge. And then you put this in, and then you solve the saddle point.
But in the end,
Yes.
the final answer is e to the power minus m times saddle point length, right?
Yes.
Now the saddle point length has a real part and an imaginary.
The saddle point length is this.
Excellent.
Yeah. And when you take m goes to infinity limit, it's just the time
That's
to
the
simplify.
real part. Yes. There's
Yeah.
no- Oh yeah, yeah. So now let's say that I ignore, because at infinity I ignore that I see.
Yes.
So it's just out.
Yes.
So the saddle point length is L horizon. I mean the length.
Yes.
Final answer sounded to me like e to the power minus m times L horizon plus I times tau s.
Yes.
Right?
Yeah.
Now, if we were looking at a real, as I'm just repeating Umbu's question. If we were looking at a real scale of this, the final answer for the 1-point function should be equal to. So presumably you mean the real part of this or something like that.
Yeah.
Okay, so that would be e to the power minus m times L horizon times cosine or sine or whatever. I'm saying sine m tau s. Right? That would be the answer. Well, first I wanted to check that was right, and second I wanted to understand why it goes to 0. Particular.
Everything is probably.
It's not exactly it. But it's quite striking the 1-point function of particular mass field this time. Why? The physical explanation. But is this a claim? Is the claim that the answer has a sign m tau in the numerator?
Like you said that there is a direction by doing not doing the political.
Right. Yeah. So, I mean, you'll find also in the original paper, they have done for a few cases 1-point function they've calculated. And the cosec result I was quoting was from Justin David and Srijan Kumar's paper, where they do the BTZ and they get like a cosec tau in the answer.
Great. One way you could imagine. Right, something like that. Yeah. But maybe there are like non-scale differences. You will see then some out that you get something in the middle. Finding.
Do they consider that? Do they consider more than geodesic going once to the singular?
Yeah, yeah.
The answer. One by. I don't know why, but maybe.
Okay.
I don't and why? You think it has some great point.
They do have some weird contours. So when you do like actual steepest descent, like a Picard-Lipschitz thing, you get some really weird contour that goes like spiraling contours.
So the final answer was that what so there are some masses for which the 1 point function goes up.
Because that force and delta you will be given are what you expect from the operation.